Okay, so this video is going to be some notes from 6.1 and then some more notes from 6.2. And I'm going to build off of the very last thing that we covered last class, which was, and I just drew this very quickly on the board. But if I said, if I give you two vectors, and in this case we're kind of assuming these are non-zero vectors so that we actually can draw something. So we've got u and v. And I want the area of the triangle defined by u and v. So this will be area of triangle defined by two vectors, u and v. Okay, so well, we learned this formula. Well, actually, here we'll just use the basic stuff: 1/2 base times height. Okay, well the base, in this case, is the magnitude of vector v. And what we need then is the height. So let me draw in the height, h. We do know how to calculate the angle between them. I'm going to call it alpha because I think that's what it's called in your textbook. By the way, this is section 4.9 in your textbook. Section 4.9 in text. So I realize the formula that we use for the angle between two vectors involves cos theta, but you can get, I mean, you'll figure it out. So, okay, so alpha's there. And if I wanted to involve the height and the u there, then I'm going to have to use sine for opposite over adjacent. So sine of alpha is going to be h over the magnitude of u. And then if I bring the magnitude of u over, I have sine alpha right there equals h. And then I can plug that in over here and get that the area of the triangle is going to be 1/2 the magnitude of v times the height, which is the magnitude of u, times the sine of the angle between them. And the angle between them, we have a way of deriving that using u and v now. And cosine. So this is the formula that gets used a lot. Typically, you put them in alphabetical order. So this would be u here, v here, sine alpha. Okay, so that's how to get the area of a triangle defined by two vectors. If I said, and you just put the two vectors end to end, and then put the tails together, and then just connect the endpoints, and you got your triangle. So if I said, well, then what's the area of the parallelogram defined by two vectors? Then really what you do is you start out with, in this case I'll try and draw them so that they look like the same two vectors, u and v. And here's the alpha between them, the angle between them. Well, the parallelogram is really if I just put another v right here and another u right there. And well, you already know that the area of this triangle is 1/2 uv sine alpha from up here. And this is an identical triangle, so the area of the parallelogram is twice the area of the triangle, so the half goes away, and you just have u, v times the sine of the angle between them. Okay, so there's the parallelogram. What I want to do now is try looking at something. I'm not going to tell you what it is yet. So I want to look at what's the magnitude of u cross v. And I think this actually, somebody might have asked this in class the other day. So let's work it out using the determinant way of getting u cross v. So I don't want to, I'm going to do the determinant by itself first. So u cross v, and the only reason is because there are way too many bars otherwise. So remember, you can calculate the cross product of u and v by putting I here, the vector j there, the vector k here, and then the little components u1, u2, u3, v1, v2, v3. And then if we work this out, if I start out with the I part, then I'm left with the mini determinant, the 2 by 2, u2, u3, v2, v3. If you've memorized the formula, that's fine too. I don't care what version you use. Then I'm going to go to my second element in the first row, and so then that one's going to be a minus, right? Remember when you're doing determinants, this one's always positive, whatever the value is, and then you alternate the signs going around. So, and it doesn't matter how big your determinant is. That first one's always plus. Okay, so it's minus j, and then the 2 by 2 that's left over, if I get rid of the column and row that j is in, is u1, u3, v1, v3, and then plus k, and that'll be, let's see, what's that? That's u1, u2, v1, v2 for the mini determinant. And then if I work this out, I'm going to get I times u2 v3 minus u3 v2, and then minus j u1 v3 minus v1 u3, and then plus k u1 v2 minus v1 u2, and okay, and then since the I is 1, 0, 0, and then j is 0, 1, 0, and k is 0, 0, 1, this all boils down to a single vector. The I component, the x component, is u2 v3 minus u3 v2. The y component is the opposite of what's in the parentheses here, so it's v1 u3. Actually, let me put the u's first just to be consistent. So u3 v1 minus u1 v3 if I distribute this negative here. And then the z component is u1 v2 minus u2 v1 if I put the u's before the v's. Okay, so I want to look at the magnitude. Okay, so I'm going to do some tricks here to kind of make the calculation slightly easier, and then I'm going to wave my hands over one part of it because it's way too annoying to actually try and work it all out. So I'm going to look at the magnitude of u cross v squared. Okay, now remember, if I just have some vector, I'll call it a, and I square it, that's the same thing as a dot a. Okay, you might remember it in this form instead, but if I square it, then you get the one above it. So u cross v all squared is really u cross v dot u cross v. Okay, so let me get rid of this stuff below. Okay, well that's going to turn into, well, u cross v is right here. So it's going to turn into this times itself plus this times itself plus that times itself. Okay, so it's going to be u2 v3 minus u3 v2 squared plus the next one squared. You can kind of imagine this is going to get pretty ugly. u1 v2 minus u2 v1 squared. Here's where I wave my hands and say, if you multiply all that stuff out and then you do some clever factoring, factoring one part of it versus factoring another part of it separately, then you end up with this line, which is pretty nice comparatively. So it's u1 squared plus u2 squared plus u3 squared, in parentheses, times v1 squared plus v2 squared plus v3 squared minus u1 v1 plus u2 v2 plus u3 v3 all squared. Okay, now this thing right here, that's u dot u. So if we use that same rule that we used originally, but backwards, this turns into the magnitude of u squared times the magnitude, oh, whoops, this square goes on the inside, times the magnitude of v squared minus, and then this thing right here is u dot v on the inside, all squared. U dot v squared. Okay, Now I'm going to use another substitution. Remember, all right, u dot v. Okay, we've got that cosine alpha rule. I'm using alpha because we used alpha in the problems above. That's u dot v over magnitude u, magnitude v. So if I multiply this over to the other side, I get the inside of the parentheses here. So let me rewrite this now as magnitude of u, all squared, that's the first term, times the magnitude of v, all squared, that's the second term, minus, and now in the parentheses, I'm going to write what u dot v is here if I isolate it. So minus magnitude of u, magnitude of v, cos of the angle alpha between the two vectors, all squared. Okay, so let me manipulate this a little bit more. So this is going to turn into u squared magnitude v squared minus, and then magnitude of v, u squared magnitude of v squared cos squared alpha right here. Now, cos squared alpha, actually, let me do one more thing. Let's factor out a magnitude u squared magnitude v squared. All right, so I think that'll make this a little bit easier. So if I factor that out, magnitude u squared magnitude v squared, then I'm left with 1 minus cos squared alpha. And you might remember sine squared plus cos squared is 1, always, of the same angle. So this guy right here is the same as sine squared alpha. So now this turns into magnitude of u, magnitude of v, squared, sine squared alpha. And remember, all this was magnitude of u cross v all squared. So I'm going to put that right here just so we have it. U cross v all squared. Well, let me take the square root of both sides. And we know that this stuff is all positive here because it's lengths that I'm working with. And remember, the angle that I'm dealing with is between 0 and pi, which means that the sine is always positive too because it's above the x-axis if you want to think of the unit circle. So then this thing is going to turn into u cross v magnitude if I take the square root. And then the square root of this side will turn into u v sine of the angle between them. And we just came up with this right here. It's the area of the parallelogram defined by u and v. So magnitude, I'll just tack it on here. This all equals the area of the parallelogram defined by u and v. Okay, so there's that. I'm going to do one other thing using u, v, and the angle in between them, and then that'll be it for notes for today. So let me see how we're doing here. Okay. So the one other thing I want to cover is something called, and this is going to be related to 6.2 now. So it's the projection. Whoa, projection. Sorry, I'm anal here. Of one vector onto another vector. So what that means is I kind of think of it like shadows, essentially. Shadows are a projection of u onto the ground, and it depends on where the sun is. So here's what I want to do. I'm going to draw two vectors. U will be the main vector. So there's u. Here's v, let's say, coming out like this. And the angle between them is alpha. And what I want to do is find something that's called the projection of v onto u. Okay, what that really means is if the sun is directly overhead from you, then you've got then the shadow of v is this part right here. Oh. This part right here. So if I figured out what that vector was that stops right there, then I'm going to call this vector right here in red, the projection of V onto U. Okay. Now the right angle ends up being the key. And so there's notation for it. Projection of V onto U, it's written as projection. Now the main thing is of V. And then to state which vector you're projecting it onto, you put a little subscript. Projection of V onto U. Okay. So let's do a little groundwork here. I'll call the length of V, I'll call that Y, and I'll call this one X, the length of the projection vector. So, and the goal is we're trying to do it all just with stuff that's written in black. So something about V, something about U, something about the alpha, and then that's it. I don't want to incorporate anything else into this. So we'll work with X and Y and then try and get rid of them. So if I look at alpha, I know that cos alpha is going to be X over Y. So then, let's see, X is going to be Y cos alpha, which is going to be, let's see, the magnitude of V times the cos of the angle in between. And we know that the cos of the angle in between is going to be U dot V over magnitude of U times the magnitude of V. And then the magnitudes cancel out here. So we're just left with U dot V over magnitude of U. By the way that your book writes it is like this. This is fine with me if you want to leave it like that. But your book writes it like this. It puts the V in front, dot, U over magnitude of U. And I think the reason the book likes this is because that, if you take any vector and divide it by its own length, that's a unit vector now. So you've normalized U. So it's V dot the normalized vector U. Okay? I'm going to pause it for a second here while I cough. All right, okay. Okay, I think that worked. All right, so let's see, where were we? This right here, the thing in the circle is X. And remember, X is not a vector here. X is just a number that tells you how long the projection of V onto U is. So, and that's this thing too. So, here, I'll write this. Note that, how do I want to write this? U dot V over magnitude of U is a scalar that gives the length of projection of V onto U. Okay, so if I wrote this, what's the projection of V onto U? That is U dot V over magnitude of U. Or if you prefer the textbook notation, V over the normalized, dot, the normalized vector of U. Okay. So in order to get, oh, and let me give a couple details about this. This is also in some textbooks called the scalar component of the projection. And so then it's written sometimes like this, comp component of V onto U. Okay. So this is really scalar component. So it's just a regular number, right? It tells you how long it is. Okay. So let's see here. What do I want to tell you about this? The scalar, so this thing right here, all right, I'll use the same notation. Component of UV can be positive, negative, or zero. Oh, hold on one second. Okay, so sorry, I lost my train of thought. It can be positive, negative, or zero. It's the length of the projection. Let's see. Oh, and the positive, negative, zero is, so if you think about it, the only way that you get a projection of zero, of length zero, is if, like, let's say this is you, and you want the projection to essentially be nothing, so that means V would have to be pointing straight up from you or straight down from you, which basically means it's got to be perpendicular to it. It could be orthogonal to it, where one of them's the zero vector, but that's sort of point. Why would you project the zero vector onto something? So it's zero. So it's zero when the angle between them is pi over 2 radians, or 90 degrees. And it's positive when alpha, okay, sorry. So it's positive when alpha, let's see here. Hold on, I gotta shut the door. All right, sorry. You'd be surprised at how often you get interrupted at 4:30 after school. Okay, so it's positive when alpha is acute, which actually means that the component of V, the scalar component, or the projection vector and U are pointing the same direction. So I'll write this. So U and projection onto U of V points same direction. And it's negative when alpha is obtuse. So U and the projection onto U of V point opposite directions. So exactly opposite. They're 180 degrees apart, basically, then. And if you wanted to justify this in your head, you can come up here and you can kind of look at this, and that should help. When alpha is between 0 and 90, not inclusive, but just between 0 and 90, you know that when you project downwards, you're going to get a vector pointing the same way. But if alpha was between 90 and 180, then the projection is really going to be back here instead. If this one's U and this one's V, then the projection's actually going to be pointing this way instead, the exact opposite. And cosine of values that are between 90 and 180 are always negative, because they're, like, if you kind of think of the unit circle, it's over here on the negative side for the x-axis. So, okay. So anyway, all we've done, though, is come up with how long the projection is. We haven't come up with what the actual vector is. Well, you know that it's pointing either the same exact direction or the exact opposite direction of U, and the sign is already included in that component calculation. So all we really need to do is take how long it is, either, you know, it, by the way, length here in this case can kind of be like -4. It just means pointing the opposite direction. So if we just take the component part and multiply it by a unit vector pointing in the direction of U. So here's the idea. Here's the idea. I've got U. Right now, I've got something pointing the same direction as U, and I know how long it is, right? So if I wanted to figure out, well, what's this actual vector, then I'll take U, I'll shrink it down or stretch it out. In this case, I'll pretend that I'm shrinking it down to a unit vector, so the length is 1. And then if I multiply that by how long I actually want, then I'll get my projection vector. So I'm going to take the, so the projection of V onto U is going to be the scalar component part that tells us how long it is and which direction it's going. Or it tells us, is it pointing the direction of U or the opposite direction of U? And I'm going to multiply it by a unit vector pointing in the direction of U. U divided by its own length. And then if I do some substitution stuff for the component part, I've got V dot u over the magnitude of u for the component, and then times u over the magnitude of u. Okay, now the bottom here, the denominator, is the magnitude of u squared. So I'll write this a couple different ways. Some people write it like this: v dot u over magnitude of u squared times u. This right here is a scalar times that vector. Okay. Other people prefer to switch out the magnitude of u squared for u dot u. And then, so this is a scalar all in parentheses, and then if you multiply it by the vector, you get a vector with a certain length, and that length is going to be what we want. Or sorry, this whole thing ends up being the projection vector. You can also switch the u dot v on top because it's a dot product. Doesn't matter the order for dot products. If it was a cross product, remember it does matter, so you can't just flip it around like that. Okay, and that's it. All right, so I doubt I'm going to ask you to derive this again. Really what I want, the main thing to pull away from it is, well, this formula more than anything is how to, oh God, is how to get the projection of one vector onto the other. Okay, hopefully that was understandable enough, and if not, well, you can ask me questions when I get back next class. All right, take care.